Yeah, so I'd just like to thank my co-authors to Tom Bishop, Brett Whelan, who are my supervisors, and Ed Jones, and Pat Holm as well, who helped with a lot of this work in the second half of the presentation. And, the first half of this presentation was really funded by CRDC, and PCT were a big help in that as well. We have a lot of on-farm and publicly available data that describes cotton farming systems now. We've got, on-farm data, operational data from attractors. We've got soil information. A lot of growers collect soil core data and send it off to the lab now. We've got a lot of proximally sensed information, such as EM and gamma surveys. But we also have a heap of publicly available data now, and that's really kind of expanded in the last 5 or 10 years. So we have soil maps across all of Australia. We've got weather information, rainfall, temperature at a daily time step gridded across Australia. We have a heap of satellite imagery available now from various satellites. So Sentinel, Landsat, MODIS, Planet, various resolutions in terms of space and time. But there's also another opportunity that there's a heap of computing power out there to process all of this data, and some machine learning methods that are quite useful in analysing it. So really talking about 2 research areas relating to this opportunity today. The first is about predicting yield potential to identify yield gaps. So, what was my yield potential? How much did I miss this by? So what was my yield gap? Where can I improve yield? And then the second part's really looking at identifying causes of yield variability. So, what's my most limiting constraint? And how can I actually close these yield gaps? So on the first one, really talking about modeling yield potential to identify site and season specific yield gaps. So we know growers are really interested in the gap between their actual yield and their potential yield. And I suppose potential yield or yield potential is really the yields that could be achieved through implementing the best management practices and varieties for their farms. But there is a problem that is really hard to get an idea of yield potential. Crop simulation models can do this. So there's been a lot of focus on using crop simulation models or mechanistic models to predict yield potential, and AppSim is a really good example of that. And there's been a lot of work done in the grains industry, not so much cotton. So basically, mechanistic models describe processes of crop growth as a function of weather conditions, soil conditions, and management. They use our fundamental understanding of plant and soil processes to simulate how crops develop. The problem is that they really rely on numerous and detailed specific input parameters. These are only usually available at research stations like ACRI. So if we go to implement them in grower fields, we have to actually simulate a lot of the input data. So it's a simulation model. We have to simulate input data. It's just simulations on simulations. So obviously some questions raised there about how accurate that is. Another problem is it's difficult to provide predictions at the density and extent to capture the variability useful for farmers. And a lot of these crop simulation models are validated with trial data that can never really achieve yield potential. Yield potential is a funny thing. It's almost like a thing that we've made up in our head. It doesn't really happen too often in the real world. So we have a wealth of data now available. It gives a really good opportunity to create empirical yield models. The advantage of empirical yield models is that they're quite flexible. You can use any data you really have available. It's built with real data, often not simulated data, and it's at a scale and resolution useful for growers. And there are some important similarities to mechanistic or simulation models. And we use this topsoil framework that we've developed, which is basically saying, yield is a function of a topography, so elevation, slope, organisms such as pest and disease, plant measurements, reflectance, vegetation indices, canopy biomass, soil, so soil types, constraints, agronomy and management such as sowing date and irrigation, and then weather information too, so rainfall, temperature, and solar radiation. So we're trying to capture all of those variables that drive crop yield. Empirical models are no longer just about getting some satellite imagery, making correlation with some yield data. It's about trying to use as much of this empirical data as possible to describe crop yield, which is kind of quite similar to mechanistic models. There's also been a real paradigm shift in precision agriculture. So we know precision ag is all about observing, measuring, and responding to variability, but traditional precision ag is really focused on single fields in isolation. But we know the real power is really in pulling together data from not just many data sources and many seasons, but also many fields and farms. And we know that different fields and farms can learn from each other. There's similarities in soil type, similarities in management, and we can take advantage of that. So the case study farm we worked on was really a collection of farms in the Guida Valley. It's a 13,000 hectare study area, and we had a heap of cotton yield data from 2002 to 2017. Our modeling approach is really about using data from all the seasons and all the fields to create one model. We used a random forest model, a ranger function for this one, and we built the model at a 30-meter resolution. So this really results in hundreds of thousands of data points when we've got 13,000 hectares, many seasons of data, and we're at such a fine resolution. It's quite a big data set in the end. The data we use for modeling, obviously yield monitor data at a 10-meter resolution, but also some predictive variables, so satellite imagery, rainfall, temperature, terrain attributes, and radiometrics and soil maps, just to capture that soil variability. We can see here that some of these variables vary in space and time, some just really vary in time, and some just vary in space. And all of them kind of have a different spatial resolution. So we kind of snap that to a standard space-time cube to account for that. And we can see that we're trying to capture as many variables of that topsoil framework as possible. So weather, soil, topography, measurements of the plant. Things like organism, pests, and disease are really hard to incorporate, but we're still trying to capture as many as we can. In machine learning modeling, most of the time, we model the yield, the 50th percentile, which is the most likely yield. But using quantile machine learning, we can actually model the upper quantile too, for example, the 95th percentile. And this upper quantile can really be seen as the yield potential, because given the combination of input variables, that is the most the yield could be for that particular location, that particular season. So Constable and Bange in their 2015 paper say cotton yield potential is 22 bales a hectare. It's kind of given as a fixed rate, but they do acknowledge that different areas of a field and different fields have different yield potential, and also that yield potential fluctuates from year to year. Farmers want to know how they can close their site and season specific yield gaps. So they really want to know their site and season specific yield potential. They don't want to know that, their potential, everything is just 22 bales a hectare. I suppose we really need a more quantitative approach to identifying yield gaps and understanding the causes of this. So the idea of using this 95th percentile, we've seen some similar work in estimating the carbon sequestration potential of soils, but also this concept called the boundary line approach, where you basically plot your yield against a covariate. For example, this is just potassium, and then you fit a line above the scatter of data points. So you're almost basically fitting the line to the max or the 95th percentile of that data. And this line really represents the max potential yield for that input level. And any points below this line are limited by another variable. So it's quite similar in concept to what we're trying to do, but instead of just using a single variable, we're using, a suite of different variables. So we use leave one field year out cross-validation to test the quality of the models. We didn't have to leave whole years out because it's not a seasonal forecast. It's really hindcasting, looking at what the yield potential was, not what the yield potential is going to be. And what we do here is we use yield data from all other years and all other fields to predict yield for that removed field for that particular season. And we actually validated at two spatial resolutions, 30-meter resolution to get an idea of within field yield gaps, and at the field resolution too, which is handy for just identifying, the mean yield gap for a field. You can see there's some pretty bad predictions in parts of the field, which we kind of expect when we've got hundreds of thousands of points. But, looking at this density plot, we can see most of the points kind of fit along that one-to-one line. Similar thing at the field resolution. The prediction quality was actually a little bit better at the field resolution, which we expect. We're kind of averaging those errors out. So 0.64 LCCC for 30 meters and 0.67 for the field scale. And LCCC is really just like the R squared, but it counts for that one-to-one line. It's not the fit of any line. So when we're doing observed predicted, we should always be using LCCC, not R squared. So this is the variable importance plot. This just really gives an idea of what are the main driving factors in general for our yield model. And see here that seasonal weather is a really strong driver of yield. So you've got rainfall and temperature, fine resolution spatial data is quite important, and also satellite imagery, as we would expect. It's nice to actually visualize this yield potential, the observed yield and the yield gaps for individual fields. We can start to pick out those patterns. See, potential yield doesn't change too much within fields. In 2009, it did a little bit, which we kind of expect this because the main driver of yield really came up as those temporal variables, so rainfall and temperature. We can see the yield gap, the observed yield here, quite a bit of variation there. But when we look at the yield gap, we can see, for example, in 2007, most of that field is hitting the yield potential, which is nice, but there's particular parts of the field where there's fairly significant yield gaps of 3 bales a hectare. We can see in some years, we're getting yield gaps of up to 7 bales a hectare, so fairly significant, but don't quite have that same spatial variability there. This is site and season specific, but over time we can just average what our mean yield potential is, what our mean observed yield is, and then we can look at the mean yield gaps to try and pick out if there's any particular locations that consistently have high yield gaps, and what might be the cause of that. It's hard to compare our approach to AppSim because it's so hard to run AppSim on a site-specific basis. We are going to compare it in some future work, but what we did here is a more traditional approach, estimating yield potential in an empirical way. So a lot of growers have, an abundance of yield data. 10, 20 years in the grain industry is fairly normal for some farmers. So what you do is you stack all of the yield data on top of each other, and that at each particular pixel of data point, you work out what the 95th percentile yield potential is, or what the max yield potential achieved at that location is. The downfall of this is that it's only really site specific. It doesn't consider seasonal conditions. To make it a fair comparison, we got the mean and the max yield potential over all years from our quantile machine learning approach. And, visually they look quite similar, which is nice to know. And there's a fairly good agreement between these more traditional approaches and our quantile machine learning approach. So in conclusion, I think it's a promising approach to identify yield potential and yield gaps that's site specific and shifts according to seasonal condition. It's definitely a more scalable approach than crop simulation models. There's been a real disconnect in yield gap research and precision ag, but there's no reason really that there should be. And this approach really had a resolution useful for growers and management. So it really points farmers and advisors in the right direction, but we need to work out how do we actually rectify these constraints. It doesn't exactly tell you what the issue is, it's telling you where the issue is. So can we rectify constraints or alter inputs to match this yield potential? And some future work's going to be focusing on doing this across a larger area, not just a collection of farms, but a collection of many farms across a region, for example, and then actually understanding the causes that are driving these large yield gaps, which is a segue kind of into the second part of the presentation. The second part's really about understanding the causes of yield variability, and we're really utilizing interpretive machine learning to do this. So we know crop yields are really affected by many spatial and temporal variables and their interaction. So the impact of temporal variables on yield, such as weather variables, are often quite directly obvious. If you get a lot of rain in a season, you get a high yield. If you don't get much rain, you get a fairly low yield. But it is often quite difficult to pinpoint the causes of spatial variables on yield. And we know that soil and terrain attributes are generally the largest causes of this spatial variability of yield in terms of within a farm or within a field. Farmers and agronomists usually have an idea of the primary cause, but it's usually qualitative and poorly recorded. We use empirical yield models for forecasting and hindcasting yield, like I showed in the first half of the presentation. But what about using empirical models to understand the primary spatial drivers of yield variation? So a big problem of this is that machine learning models are like black boxes. Traditional inbuilt methods, like I showed previously, that variable importance plot, have many limitations. These global methods just show the overall importance for the model. There's no real insight into what is driving yield in particular locations of the field. And this is a real limitation, as a variable may not impact yield across much of the data set, but it might be a really important factor for a subset of the data set. So interpretive machine learning techniques such as Shapley, additive explanation values are an opportunity to overcome this limitation. And they really have the ability to identify which variables contribute to increasing or decreasing yield at specific locations, how much they impact this in bales a hectare, which is nice, and also their relative contribution. So it really aids in identifying the causes of low crop yields and can inform decisions on what management interventions need to be made to close those yield gaps. So another common problem when assessing drivers of empirical models is that variables are not directly interpretable, often used to model yield. So a good example of this is using an EM map or an ECA map in a yield model. So we know it often really highly relates to yield, but it's hard to understand how this impacts yield. So it's important we do some feature extraction and transformation of our variables, and we really need to use easily interpretable predictive variables to aid in understanding driving factors of yield. So a good example of this is EM map here. What does ECA of 200 mean? Not too many people know. Whereas if we do some digital soil mapping, join that with some soil information, soil core data that's been analyzed, we can create a map like this, which is a pH map showing the depth that a specific constraint threshold is met. So it's much more easily interpretable for growers, agronomists, and researchers to understand what's driving yield there. You know, a lot of people just, when they use machine learning models, it's just about throw everything in and see what comes out. But it's really not about that anymore. It's about, creating some easily interpretable variables and utilizing those. So the specific study area and data set was collected by Pat Holm and Ed Jones, Cubby Station, Dirranbanya in Queensland. They've got 8 flood irrigated fields here, 2,000 hectares, and they collected 75 soil cores to 1.4 meters. So a pretty good data set. And the sites were selected not just randomly, but using a conditioned Latin hypercube, taking into account the variation in EM, approximately sense gamma, elevation, bare soil redness, and things like that to make sure we had a nice widespread data set that captured the variability. So the soil cores were analyzed for pH, ESP, ECE, and texture. And, for this particular study, we focused on the whole farm, but we also focused on one field as a case study, which is just this field here. So the spatial data sets we used in our yield modeling included pH maps, ECE, ESP maps, and these digital soil maps were created with the same covariates. So EM, gamma, elevation, and things like that, and some satellite imagery. So instead of using kind of traditional soil maps where we create, pH from 0 to 5, pH from 5 to 15, pH from 15 to 30, and so on, we've used these depth to constraint maps, which is showing, this is the depth that we are reaching a pH constraint of 8, a depth we're reaching an ECE of 10 decisiemens a meter, and the depth that we're reaching an ESP constraint threshold of 10%. So we're kind of condensing all of that information from the whole profile into a single variable. We also had some important terrain infrastructure variables too. So closed depressions, showing where there's little holes throughout the fields, the distance down the furrow, which has some important implications for moisture, and then the cut and fill map to the original cut and fill map, which is pretty handy because we know, high levels of fill and high levels of cut can have some negative impacts on yield. So all of these maps were created at a 20-meter resolution, so fairly fine resolution. So the first step to use this interpretive machine learning is to just build a machine learning model. And we used XGBoost here, gradient boosted decision tree models, fairly similar to random forest. So, yield is a function of ESP, pH, ECE, the holes, the distance to head ditch, and also the cut and fill here. And we used tenfold cross-validation to assess how good our models were. And we can see here that the fit is pretty good. So it really just shows that the predictive variables in the model can describe yield quite well. For each individual field, we built a model, and here we've aggregated that to the whole study area. So we can see the LCCC is 0.9, which is very good. RMSE 0.7 bales a hectare, which is fairly low. But for the case study field, LCCC of 0.68, RMSE of 0.83. So a fairly good fit. This is the distribution for each of the fields for the RMSE and LCCC. Some fields weren't as good, LCCC of 0.5, but some were kind of up to 0.75. So a bit of a variation there for each field. So the next step really is to use interpretive machine learning to identify the local primary spatial drivers of yield. We use SHAP values for this. We calculated SHAP values. So SHAP's good because it really provides local model explanation and the contribution of each predictor to yield for each data point within the data set. SHAP values are calculated for each point in the training data set, and the sum of each variable SHAP values is the deviation from the field average. Here's an example for one data point. If this is showing in bales a hectare, how much that variable is contributing to yield. So whether it's contributing negatively or positively. You can see for this particular point, the distance down furrow is positively impacts yield. The cut and fill level negatively impacts yield. ESP negatively impacts it, so does pH, so does closed depressions, and ECE does not have any particular impact on it. So if we added all of these values up, I think it adds up to about -2, which means if the average for the field was 14 bales a hectare, this particular prediction for this point would be 12 bales a hectare. So the variable that most contributes to decreasing yield, so the most negative SHAP value for each location was mapped. We can see here for the whole study area. Look, using 6 variables, it's a little hard to interpret it, but if we focus on just a particular field, we can see, okay, this part of the field, the most negative impact on yield was from closed depressions. This particular patch here, the most negative impact on yield was ESP. So I think these maps here are better for understanding impact and the magnitude of each variable on yield. So viewing SHAP maps, which are these things here, ranging from red to green, really with the maps of predictor variables, helps to understand the causes of spatial variability, and we can actually determine whether this is logical or not. Just looking at this first one, closed depression, so anything that's that yellow color is not really being impacted. The yield isn't being impacted. We've got some patches here where there's quite a big negative impact on yield, 1.5 bales a hectare. And when we go to look at that corresponding closed depression map for the field, we can see there's big holes there. So that makes a lot of sense. You know, distance down furrow, when there's a long distance down the furrow, it's had a positive impact on yield in this particular season. I think that's really just going to relate to soil moisture. Moving on to cut and fill, we can see areas, you know, big negative impacts on yield there. It was a massive fill area, but also areas where we have large cuts, it's also negatively impacting yield. Whereas there's kind of in the middle, there's not so much of an impact on yield. In terms of soil constraints, when we're reaching a pH constraint quite shallow in the topsoil, this yellow patch here, we can see it's having a negative impact on yield. When we're reaching a pH constraint quite deep in the soil profile, it's having a positive impact on yield. There wasn't much of an impact of ECE on yield here. That's just because any constraint was kind of reached quite deep in the profile, and pH and ESP is a bit shallow in there, so that's the most limiting constraint. If we move to ESP, we can see it's having a big impact on yield. So when we've got these patches here where a constraint's being reached right in the topsoil, we're having a big negative impact on yield. And the same as pH, when we're seeing a constraint quite deep in the soil profile, it's having a positive impact on yield. So all of these maps quite useful for creating management, implementation of management practices. In conclusion, I think visualizing SHAP values into maps showing the variables most negatively impacting yield ease the interpretation of the results. Using easily interpretable predictor variables is also really important for the analysis. I think if we just shoved everything in, it wouldn't be so interpretable if we were just using things like EM and satellite imagery. Using interpretive machine learning really is a promising approach for identifying the primary spatial drivers of yield within fields, but also quantifying the magnitude of yield loss caused by each variable. And I think it really is a more quantitative way to aid growers and agronomists to implement management strategies to overcome these primary limitations of yield. And future work looking at these maps of the impact of individual variables on yield means that growers can really determine the cost benefit of an amelioration strategy. So, what is the cost of gypsum to ameliorate that constraint versus, what's the benefit of the cotton yield increase over a number of years? So yeah, more future work will be looking at implementing this across multiple seasons, as we know that the main spatial drivers of yield fluctuate from season to season. depending on temperature and water availability, and we'll also include some spatial and temporal variables when we do that. And that is it. Thank you.